Let's see how fast I can do this without being too confusing. Calculate the PI of a peptide. This is a pentapeptide, meaning that it has 4 amide bonds. I'm going to draw it how I would predict it would look like at pH 1, which is the fully protonated form. pH 1 is acidic enough to protonate the N-terminus, making it positively charged. We have 5 amino acids. The first amino acid at the alpha carbon, the R group would be wedge, going up. The way I draw it, in this zigzag motion, the second amino acid would have its R group on a dash. Now, why does that look strange? Oh, I forgot the N. Okay, good. Third amino acid would be wedge. Fourth amino acid would be dash. Last amino acid would be wedge. At the C terminus, pH 1 is acidic enough to protonate the carboxylate, making it a carboxyl group. pH 1 is not acidic enough to put a hydrogen here, so do not do that. Asparagine, which is the first amino acid, has a CH2 group and the amide. The amide will not be protonated or deprotonated between the pHs of 1 to 13, meaning that it will always stay neutral. The other thing that I would be watching for is that you put a bend at every sp3 carbon. So you need to put a bend between the wedge and this line. Histidine, second amino acid, has a CH2 group, I believe a double bond at N here. Then we have an N here, doubly bonded. It's a 5-membered ring. A lot of the charts for amino acids have this ring neutral because at pH 7 that ring is actually neutral. There's a hydrogen here always that will never be removed, and you will never protonate at that nitrogen. At very low pHs you will protonate actually this nitrogen here because of resonance. By putting the plus charge there are resonance structures that can help stabilize that plus charge. Namely, the lone pair goes here, the pi bond neutralizes the nitrogen. That's what it looks like at pH 1. Next is tyrosine. Why tyrosine? I purposely made a fairly difficult peptide. Difficult in the sense that sometimes students don't know what protonation state to draw the R group in. Tyrosine is one of those amino acids. Tyrosine has also a CH2 group and has this OH. pH 1 is not acidic enough to put another hydrogen here and make it positive. So don't do that, just like you would not do this. Don't do that either. Between the pHs of 1 and 13, the tyrosine OH will never become positive. But at some point between the pHs of 1 and 13, this will become negative at some point. I believe that that's true because tyrosine has a pKa value for its side chain We see that right here, 10.1. Next, proline. Proline is a ring that uses the nitrogen of the amine group, and it's a 5-membered ring. I have it dashed already here, okay, and that is true. But to make a 5-membered ring, we would use this nitrogen and close it like that. Now it's neutral. An amide is going to be neutral at any pH between 1 and 13, so we got to get rid of this H to make that nitrogen neutral. That's how you would draw proline. At no pHs between 1 and 13 will this ever become protonated because it is an amide. Amides will never lose a hydrogen or gain a hydrogen between a pH of 1 and 13. Glutamic acid. Glutamic acid has 2 CH2 groups. One there, second one there, and then a carboxylic acid group. Just like this, carboxylic acid is protonated and neutral at pH 1. Same thing for this group here. That is glutamic acid. I drew this at pH 1 because at some point, as I raise the pH, I'm going to start taking off hydrogens. That one, that one, that one, that one, that one. How do I know I'm going to take off a hydrogen? We're going to look at the pKa values here. No, where'd it go? Oh man. Yeah, it was this one. Okay. We're going to look at the pKa values here and start listing them. Asparagine, the first amino acid, the amino group. The amino group is asparagine. It's 9.8. I'm going to circle them actually. So asparagine, we definitely need this number here. We do not need this number because there is no carboxyl group anymore because we made an amide, and there is no side group. Let's put that in 8.8. Again, there is no pK for this. Next one, histidine. This one you've seen many times probably, but a circle what pKs we need. Histidine is a basic amino acid, and we have here 6.0. We don't need that. We don't need that. Okay. Next we have tyrosine, the side group of tyrosine. We have 10.1. We don't need that. We don't need that. Proline. Proline has no R group that can be ionized. And we can double check. See, there's nothing there. We don't need that. We don't need that. Next is glutamic acid. So we do need the side group of glutamic acid, 4.2. The carboxyl end is exposed, so we need that one, 2.2. The amine is no longer an amine, it's an amide. 4.2 and 2.2. 4.2, 2.2. Okay, I said at the beginning I'm going to do this as fast as possible. For the PI, you're going to need to know the pKa's that sandwich the neutral, fully neutral peptide. The PI is literally the pH at which you have the most peptide chains that have a net neutral charge. At pH 1, we have a charge of +2. Okay? And so, let me show you how I would do this without having to draw all these structures. +2. The first pKa we cross over as we increase the pH is 2.2. And so here is pKa 2.2. We cross over it To get to pH above 2.2, we will randomly choose pH equal to 3, but it has to be less than any of these other pH. It has to be less than 4.2, which is the next pKa. Okay? So at pH 3, we are basic enough to remove this hydrogen here. Okay? So what I'm going to do is I'm going to put a little check mark here. Let me use a different color. Let me use this one here. Check mark there. And this becomes a negative. And so at pH 3, what do we have now? Positive, positive, neutral, negative, neutral. So the positive and negative cancel out. We have a +1. And you will find out that every time you cross over one pKa border, you are removing a charge, a charge. You're getting more negative. Next pKa is 4.2. I'm sure you could, if you do this a couple times, you'll find faster shortcuts. Let me do pH equal to 5, because I don't want to go over 6 now. I want to go in between those two. And now my now my charge is, well, we're going to take off this hydrogen. We're going to take off this hydrogen also, and we take care of that. Okay, so the charge of pH 5 now is positive, positive, neutral, negative, negative, net neutral. You need that. Like that. Next, pKa to go cross over is 6.0. So we are now here. We are going to remove this and become neutral. Okay? The histidine becomes neutral. And so pKa is 6.0. So what pH do we want to use? Let's use 7. That's above 6, but below 8.8. Okay, so 7 is okay. And now that we've taken off that hydrogen here, what do we have now? Positive, neutral, neutral, negative, negative. So the positive and negative cancel out, but we have one more negative. That's -1. You could go further, okay, but I already found the net neutral species here, right here. So you are really focused on this area of the pH range. And it makes sense now if you take the midpoint between 4.2 and 6.0, you will have the majority of the chains, as many as possible, be a zero charge. Okay, so it is an average, and it is the majority or the predominant form. It's not 100%, okay, because when you cross over the pKa, you don't automatically get 100% of the deprotonation. There's a range. Anyway, the Pi equals 4.2 plus 6.0 divided by 2. So that's what, 10.2? So that would be 5.1. That is the pH where the most chains are net neutral. We call that the Pi. Now you could keep going. You could go to what? We still have to deprotonate here. And we still have to deprotonate here. Ultimately, what you could get is a -3 charge, I think. That becomes neutral, neutral, negative, negative, negative. That's how you figure out the Pi, or that's how I would figure out the Pi. Now, the thing is, and then I'll let you guys go, what if they ask for draw the peptide at pH, I don't know, pH 9, okay? What about pH equals 9? What is the shortcut there? The shortcut there is you have these numbers, okay? and you have it at pH 1 in purple. At pH 9, you are basic enough to remove one of these hydrogens. So this becomes neutral. This becomes neutral. 9 is not basic enough to get off that hydrogen, so that stays neutral. 9 is basic enough to make that negative and to make this negative. So you're copying this chain, and again, this will be neutral, 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 negative, negative.